This is lecture 7 for week 9 of CS 1030. So far in the lectures for this week, we've looked at converting between forms of a circuit, and we've looked at sort of how we can kind of do simple tasks using circuits. What we're going to do for the rest of the week is look at how we can build up more complex circuits using the simple components that we've already seen so far. And what we're going to see is that we can actually, sort of using fairly simple collections of components, we can do pretty interesting things. And the first task that we're going to look at is adding binary numbers. So let's take a look at that. So the circuit that performs addition for binary numbers, and here we're looking at two 4-bit numbers, is called an adder. And it looks pretty complicated at first, and it sort of is at some level. But what we're going to see is that we can break an adder down into pretty simple pieces. And then once we understand the simple pieces, we can put them together in a pretty easy way to create adders. So let's talk about how adders work for binary numbers. Well, they work just like you would do it. And if you remember, we looked at this sort of earlier in the semester. You start at the least significant column of bits, and you do binary addition. And then from that column, you possibly get a carry out to the next column, and so on. And this is how addition works. And if you remember, the algorithm is basically very, very similar to the one you learned for adding decimal numbers in school. We're just doing binary addition instead of decimal addition, but the sort of high-level algorithm is the same. Okay, so we're going to first look at is how to add a single column of binary digits. And here's the truth table. So if we want to add 2 bits that have values A and B, we're going to have 2 outputs. There's going to be a sum, which is the result of the addition, and then there's going to be a carry output, which is the possible bit contributed to the next column over. And here's the truth table for these. And if you sort of remember how we've talked about circuits in this course so far, we've always talked about a circuit as having multiple inputs, but a single output. And here we're looking at a circuit with multiple outputs. So the way to think about this is, it's not a single circuit, it's really just 2 circuits sitting next to each other. And then kind of for convenience, we refer to it as a single circuit. But really what's sort of sitting behind the scenes is a single circuit. Okay, or sorry, a pair of circuits. Okay, so the circuit that does this part of an addition is called a half adder. So it does a single bit addition and computes the sum and the carry. And so let's look at a half adder here. So here's the truth table. And we want to make a circuit that implements this truth table. And when we looked at conversion between different forms of a circuit, the one case we didn't look at is this one. It's coming up with a circuit that corresponds to a particular truth table. And the reason that we didn't do that is this is a more involved topic. It's a little bit more work, and we don't want to get into it in 1030. If you, there's certainly plenty of other courses where we get into this kind of stuff, but it's not this one. But it turns out that in fairly simple cases, we can basically just look at the truth table and eyeball it and find a logic gate or gates that implements it. And that's going to be the case here. So let's look at the sum column first. So this is the behavior we want. And the question is, what logic gate or combination of gates it provides that behavior? And here it's easy. It's just an XOR, or it's just an exclusive OR. So if the inputs are 0 and 0, we want the sum to be 0. If the inputs are different, that is to say, one of them is 1 and 1, 0, we want the output to be 1. And if the inputs are 1 and 1, we want the output to be 0. And again, that's exactly what exclusive OR does. So in the logic diagram for a half adder, all we do is connect inputs A and B to the inputs of an exclusive OR gate, and the output is the sum. It just works. The exclusive OR gate does exactly what we need, and so this is how we this is how we could build a half adder for real. Okay, now for the carry part, we need the behavior where we need a logic gate which makes it so that the output is 0 in all cases, except where both inputs are 1, in which case it should output 1. And so if you think about all the logic gates we looked at, which one actually does this? And it's an AND gate. An AND gate has exactly this truth table. And so if we want to implement the carry part of a half adder, all we need is an AND gate. So here we have an entire half adder. It has inputs A and B. It uses 2 different logic gates, an exclusive OR and an and respectively, those exactly compute the sum and carry. So we're basically done with a half adder. So that's pretty cool. It turns out a half adder is not really hard at all to build using a circuit. So now let's look at why is it just called a half adder? Why make this distinction between a half adder and a full adder? So to understand what's going on here, let's look at adding 2 binary numbers. So we have 2 3-digit binary numbers here, and let's do the addition. So we start at the least significant bit column. So we add 1 and 1, and this job a half adder could do. A half adder can compute that, and we just saw this on the previous slide. A half adder can compute that the sum bit of adding 1 and 1 is 0, and that we carry out a 1. Okay, so now we're in the next column. We're in the second least significant column. And now we can't do this with a half adder. We can't do it with a half adder because a half adder adds only 2 things, and we have 3 things. So the half adder doesn't solve this problem, and it also doesn't solve any of the other bits. So it's going to turn out that we can fix this using just a little bit more circuitry, and that's what we're going to look at in the next lecture segment.